Hello everyone, thank you for watching this video. My name is Rafael and today I'm going to talk about our work on instance segmentation targeting biological images. Instance segmentation is the task of partitioning an image into individual objects with pixel-level masks. It presents several challenges. Unlike semantic segmentation, the number of objects per image varies, which means we cannot simply use a model with fixed number of output channels. Labels are also permutation invariant. Both examples shown on the right are equally valid solutions. Depending on the task, the object size can vary. For instance, the area of the leaves shown here varies by tenfold, which needs to be taken in account in the training objectives. In addition, biological images present specific challenges. For instance, when processing large images by tile, labels need to match at the seams. Increasing the patch size to speed up inference is also not always trivial. This example shows label predicted on the same patch size as the training set. However, it completely fails when predicting larger image because the network learned to rely on borders during training. Volumetric data are also very common. Simply swapping 2D convolutions in the standard model for 3D ones often require more memory than available, even when training with a batch size of 1. It can even be a problem during inference as substantial overlap is needed between tiles. Volumetric data also typically have lower resolution along the depth than laterally. For better memory efficiency, it should be addressed by the network architecture rather than by resampling. To address these challenges, we propose RDCNet, a recurrent architecture that gradually refines its output and can generate visualizable intermediate results. Two heads are attached. The first outputs semantic classes, while the second outputs embeddings that partition the semantic mask into instances. In the following section, we first focus on the design of the network. When it comes to pixel-level mask prediction, the UNet architecture is probably the most common choice. Over the years, several improvements have been proposed. For example, stacked hourglass introduces global context earlier by stacking smaller UNet-like networks. More recently, Recurrent UNet followed a similar approach but reduced the weights at each iteration. While improving performances, each modification also introduces additional hyperparameters, which often need to be tweaked on a project basis. This can, for instance, mean changing the depth of the network to achieve a particular field of view, or adjusting the layer distribution to avoid out-of-memory errors. Taking these insights, we aim to build a simple architecture from the ground up that tries to decouple the network capacity from other design choices. We started with the idea of pooling network resources into a single large recurrent block. While a single conventional layer applied recurrently kind of works, it is not very efficient. First, processing the full resolution image at each iteration is expensive and not necessary. We therefore add strided convolutions as learnable down and upsampling layers. It is also useful to compensate for 3D anisotropy and leave an approximately isotropic feature set to be processed by the recurrent block. The recurrent block itself follows a residual formulation to avoid vanishing gradient over multiple iterations. It takes the feature set of the previous iteration as input and only predicts an additive update. Since it is at the core of the network, the recurrent feature set has to be substantial. To increase the number of channels in the recurrent block without an exploding number of parameters, we use a group factorization trick and add a pointwise convolution to mix information between groups. Finally, we introduce early global context by using 3x3 dilated convolutions. Instead of arbitrarily choosing a dilation rate, we apply the same weights at multiple scale and combine them with a learnable pointwise convolution. In edge cases, the network could learn during training to use only one dilation rate, or inversely, apply the same filter at different scales. To train the network for instance segmentation, we integrate a few recent works to our framework and apply losses on the final output. The semantic branch is trained with a soft checkered loss as it directly minimizes the intersection of a union and deals with class imbalance. The instance embeddings branch requires a few extra steps. For each instance, a center is determined by taking the mean embedding over the instance mask. The embedding distance to the center is then transformed into a probability map by passing through a Gaussian. These instance probability maps can then be treated the same way as the semantic branch. The inference differs slightly from training. We first need to take a step back and look at how the semi-convolutional output is generated. The raw network output is an offset vector that points to the instance center. It can also be represented as horizontal and vertical displacement fields. Adding the image coordinates create uniform regions that separate instances along the vertical and horizontal axis. If the image has to be processed by tile, the image coordinate of the patch are replaced by the coordinates of the full image, thus producing seamless embeddings. From there, instance centers are determined by a simple Hauff voting scheme, and each pixel embedding is assigned to its closest center to form the final labels. This animation shows the displacement field and vote counts as the number of iterations increases. At first, each pixel votes for itself, before gradually pointing towards the instance center. We tested our framework on 3 different datasets: 3D nuclear segmentation of intestinal organoids imaged with a light sheet microscope, a benchmark leaf segmentation challenge that presents intricate shapes, and a multi-organ nuclear segmentation challenge on H&E images. The chart shows the F1 score versus overlap threshold between prediction and ground truth masks for stacked dilated convolution layers having different dilation rates. A dilation equal to 1 corresponds to a single 3x3 convolution. Overall, extra dilation rates provide early global context and improve performances. The exception in the organoid dataset is likely due to the receptive field being too close to the training patch size. In other words, the network expects padded borders that are not here during inference. Similarly, we also look at the effect of varying the number of iterations in the recurrent block, which can be assimilated to varying the depth of the network. Major gains are obtained by increasing the number of iterations up to 5 before reaching a plateau, which makes it a good compromise for practical applications. Finally, we compare our performance against relevant works and reference architectures. We achieved the best results on the leaves and organoid datasets while being competitive on MonuSeg, and still outperforming interhuman agreements by 2 points. We also show consistent improvement across all datasets compared to a baseline unit trained with the same loss function. To summarize, we have presented a minimalist recursive network for instance segmentation in biomedical images. We hope that the limited number of hyperparameters and interpretable intermediate outputs will help its application to a variety of datasets. In particular, 3D datasets where the recurrent architecture makes it an ideal candidate to process large volumes at once. Thank you for watching, and please check out our GitHub page to know more.